Okay, here we are again. So we were not completely done last week with our discussion about the binomial option pricing model. I seem to remember that we may have gotten through a couple of European examples, but not an American examples. So we'd like to change that right now. So there's one of the spreadsheets that I sent you is called the binomial option pricing examples. And so it has one of each, an American call input, a European call input. And so what we want to know is how are they different? Now, we derived the formulas last week, and it took quite a while. That's one of the reasons why we never finished. But it's important that we understand how the tree works. And then the formulas will give us the numbers that we're looking for. But when we come to the American call options and the American put options, we have to take into account the fact that they can be exercised early. So our strategy is a little bit different for pricing them on the tree. But the basic logic hasn't changed. Let's go back to the slides for a second and session 6 and just quickly review what we were doing there. Specifically, the formulas for the binomial option pricing model. That's what we're interested in right now. Let's see, somewhere down here we have our formulas. Now, we already remember from last time that the stock price goes either up or down by a fixed constant, which we call U or D, and it always goes up or down by the same amount. So that, for example, if I go up 2 times in this simple example, I'll reach the node where the value of the stock is U squared S, because that's just US times U. If I go down after reaching US, I'll reach DUS. And the same thing is true if I go down to DS and then back up again, I'll reach DUS. If I go down twice, I'll end up at D squared S. Okay, so these are multipliers. U and D are multipliers, which we apply to the current stock price to populate the stock price tree. The option tree is completely different. These subscripts are not multipliers. These are just there to remind us what node we're at. So, for example, FUU does not mean that its value is F times U times U. Okay, it means something very different. And in fact, the option prices on the maturity date are all equal to the payoffs based on the stock tree. So I think I have another diagram that shows that. If not, I can put it in here right now. So yeah, let's do that. Hold on. So here FUU would be equals max. Oh, wait a minute, I just realized this is meant for any option. If it's a call, all right, I'll tell you what, let's do this. Let me create 2 separate diagrams here. So in this first case, let's say this is a call. Okay, so this would be max. Now, normally, as you know, the payoff to a call option is max S minus X and 0. Here it'll be the maximum. Actually, here we're using K. Sorry, I forgot. Okay, so we'll have U squared S minus K and 0, because that's the value that the stock will reach if it goes up twice. Okay, for this one, we'll have the max of DUS minus K and 0. And down here, finally, we'll have max D squared S minus K and 0. These are the easy ones, okay? These are the so-called payoffs or intrinsic values to the option, because that's the maturity date of the option. For the put tree, we just change these. For example, this one becomes the max of K minus U squared S, comma 0. This is the max of K minus DUS and 0. And then finally, this is the max of K minus D squared S and 0. And again, just a reminder, the payoffs are never negative. So that's why we have this max argument here. It means that it's the greater of these two, depending on which one is positive. Now, the interior nodes are a little bit trickier. In fact, once we have calculated those payoffs, what do we do about the interior nodes, as they're called? I'll tell you what, let me draw another picture here just to remind you how this works. And this part doesn't really depend on whether they're calls or puts. What we have to do is go through each node. Okay, so let's say, for example, this is our tree for the call option. Okay, so this is, we already know these. All right, this one is, of course, the payoff at this node. Well, actually, you know what? I just realized something. I just want to make it clear here that SU squared and U squared S are the same thing. The order in which I write these doesn't make any difference, but I want to be consistent with what I was doing earlier. So I'll tell you what, let me change this a little. U squared S, U ds, and then we could call this last one D squared S. So what about these other ones? Well, the so-called interior nodes, like for example, this one is F subscript U. And what do we do about that one? Well, FU, first we always start with the present value. And also don't forget, there's implied probabilities on these branches. P is the risk neutral probability of an upward movement. 1 minus P is the risk neutral probability of a downward movement. So what I need in the brackets is the expected value of the option in one time step. So in other words, we'll have P times FUU plus 1 minus P times FUD. Now, why did I choose FU and FD, FUU and FUD? Because if you're here, those are the two nodes that I can reach. If I go up, I'll reach FUU. If I go down, I'll reach node FUD. And the probability of going up to FUU is P. The probability of going down to FUD is 1 minus P. So in brackets, we have an expected value, and then we discount that with the risk-free rate of interest to come up with the price of the option on this node. Now, keep in mind too, these are all European examples. Let me just remind you that we haven't actually looked yet at how to calculate the price of an American option. So these are European options. Let me just make that crystal clear here. And then FD, based on the same logic, will be, let's see, I don't think I have enough room here, so let me do this. E to the minus R delta T. Now from here, if I'm already down here, if I go up, that will bring me to node FUD. And if I go down, that will bring me to node FDD. And then I've got one more step, that would be F. This is what I'm ultimately interested in. And so I'll do the same exact thing. If I go up from this node, I'll reach FU. And if I go down, I'll reach FD. And so that's how I ultimately calculate the price of this European call based on this tree. Once I've filled in the payoffs or intrinsic values on the maturity date, I don't really need to look at the stock price tree any longer, because the entire tree is determined by the probabilities, the risk-free rate, and what comes at the next node. Now, of course, if I did have a European put, the logic here is exactly the same. The only thing that changes from a European call to a European put is the the payoff. The rest of the tree is exactly the same. In fact, here's what I'm going to do, just because I can. I'm going to save myself a lot of time here by not rewriting the whole thing for European put. I'm going to replace these, and the rest can stay the same. All right, so here I would have K minus U squared S, K minus U ds, and K minus D squared S. The rest is exactly the same. Okay. Now we do have an Excel spreadsheet here where all of this is set up for us. Why don't we go ahead and start looking at these examples? And you can see, you know, if you set it up correctly, you can do this in Excel without doing a lot of calculations. All right, so remember, it's called binomial option pricing examples. So sheet 1 is a European call. And I think this one was taken from the slides. Let me just go find it. I think this is it. European call. Now the stock is selling for 100. It's a 1-year option. Oh, I see. This is a 1-period model. It's very simple. So we can, but that's okay. It's exactly what I just showed you, except with one time step. So yes, this is the one. All right. So what I did here was I went through and I calculated the values that we'll need. Now we need to know, U and D were given to us. These 4 values we actually need to calculate ourselves. This one is the present value of $1 based on the risk-free rate of interest. This is the future value of $1. This is the risk-neutral probability of an upward movement. And this is the risk-neutral probability of a downward movement. And these P's obviously come from here. So P is this formula. And this is simply 1 minus that. So these will give us all the information we need to come up with our populator tree. This part was given in the formula. This is what we're after. So you can see with this very simple 1-period model, at time t equals 1, the option matures, and therefore its value will equal its payoff or intrinsic value. Now, since this is a call, in this first case, that would be the maximum of SU minus K and 0. And that turns out to be $5 because S times U is 105 and the strike price is 100. So that means you'd have a payoff of $5 in this upstate, but now down here, the price goes down to 95. And that means the option will not be exercised and the payoff will be 0. So this cell is this formula right here. So I've got the present value, B7, times, and in parentheses, B9 is the probability of an upward movement. The H4 is right here. This is the value of the option if we go up. Then we have B10, 0.19545 times the probability of going, the value if we go down, which is right here. And so here it's really quick and easy. This tells me that the call price is approximately $3.90. And it is based on these formulas. It's just that unlike the graph I was just showing you, this is only a 1-period model. But we can easily extend it to as many periods as we need. All right, now what about a put? What if this same exact option had been a put? Well, like I said before, the only thing that would have changed is right here. The payoffs are different. And in fact, in this case, they're reversed. Instead of 5 and 0, they're 0 and 5. But look what a difference that makes to the price. Okay, so now we're still using this formula. But now when we go to the upstate, we have a value of 0. And in the downstate, we have a value of 5. And since the probability of moving up is very high, that means that the value of this option is quite low, less than $1. Okay, so there it is, roughly 95 cents. All right, now in the next sheet, we've got a 2-period model. It looks like it's the same one. Let's see. There it is. All right, so in this case, the stock is selling for, oh, I see what happened. Oh, I didn't realize I had done this. These are not the exact same numbers. We can change that though. Yeah, I wonder why I did that. Let's see what happens if I change this to 102. It should give me the same results. Yeah. Wow, that was weird. Yeah, no, that's it. Okay. All right, well, let's do that. But you see how easy it is to make that kind of a change in Excel. So for some reason, I use 100 in the slides when in this, on the spreadsheet where it's actually 102 in the slides. So that was kind of stupid, I thought, but it's fixed. Now you can see we've got the same basic information that we had before. It's exactly the same problem, except now it's a 2-period model. In other words, we're assuming that, just to keep it simple, this is now a 2-year option with 1-year time steps. So there's 1 year separating each of these time steps. And so the stock price tree is populated. This is S times U, this is S times D, and U and D are given over here. And then this is SU squared, SUD, and finally SD squared. That's the easy part. Then we come over here to the tree, the option tree that is, and we always start here at the maturity date and calculate the payoff or intrinsic value to the option. Here the time is T equals 2. And so in the upstate, or actually what I should say is when we go up twice, here's the stock price. The strike is 100. So you can tell pretty quickly that all you have to do here is subtract 100 from this price, and you've got 12.455. Here the stock price is 101.745. You subtract 100, and the option price is 1745. Down here, the option's out of the money. The stock price is under 100, and so we end up with 0. Now here we use this formula that we've been using before. It's the present value of P times FUU plus 1 minus P times FUD. We always start with the present value, e to the minus R delta T. Inside the brackets, we have the probability weighted average of the upstate and the downstate. In other words, P times this FUU, 1 minus P times this FUD. Same thing here. And when you work your way back in the tree, we get an option price of approximately $8.10, 11 cents. Now, the put, same thing. Just like I said before, everything is identical between the call and the put, except right here. The payoffs are different. The high payoffs are down here at the bottom. The low payoffs are up at the top. The internal formulas, these internal nodes or interior nodes, are exactly the same. And you can see the put here is only worth about 42 cents instead of $8.11. All right. Now we're ready for the American option. Now this is where it gets interesting. What do we do differently with American options? Now here, the price is 100. So we're back to 100. And in the slides, we start with a put, which is okay. I've also got the equivalent call up here. The price is currently 100. It's a 2-year put. The strike is 100. These are the data we're given. And the filling in of the tree is exactly the same. Oh, I see what happened. This is back to a 1-period model. Okay. We've got the, okay, good. This is the 1-period model for the American call and put. So in other words, this tree is the same one we had back here. And this one, interestingly enough, the payouts are exactly the same. So here's what we have to do. So this is the logic behind what we're going to do. For all of the interior nodes, which is as they're called, that's okay. What's going to happen here is this. It's no longer enough to use this formula. So what's going to happen here is this. Suppose we look at this point right here. Let me see if I should do this in the slides instead of here. Oh, sorry, this is the 2-period model. I need to find a slide here where I can put in the new information. Okay. Oh, this will do. All right, so here's what's happening. So here's an American call, and here's American put. What I'm going to do differently is this. For each node, each interior node, that means the nodes that how would I describe this? At each interior node, the nodes at all times, except for the maturity date, we must consider whether or not it makes sense to exercise the option early. That's what we have to decide. So in other words, at each node, we're not just using a formula now. Well, we are and we aren't. I mean, we still are, but we have to make a decision at each node now. Now, how do we know if it makes sense to exercise early or not? Well, if we choose not to exercise the option, it will have the same value as an equivalent European option. if we choose to exercise the option, it will have a value equal to its payoff. So logically, then, our decision will come down to which of these two gives us the greater value. In other words, we want to make sure that the value of the option is always as high as possible. So therefore, the way this is written, the only way it makes sense to exercise the option early is if the payoff exceeds the value of the equivalent European option. So, for example, let's see. See if I can come up with an example here. Suppose this is an American call. And so this is node FU, which means that the stock price is SU. If this was in a European call, it would be equal to e to the minus r delta t, p times FUU plus 1 minus p FUD. Okay, we've already seen that this is the value of the option if it is European. In other words, the value if not exercised. On the other hand, if it's exercised, it'll be the max of US minus K and 0, which is the value if exercised. Now, because we assume that investors are rational, the option will only be exercised if US is greater than K. Or think of it as US minus K is positive. So what we're going to do is claim that what we're actually comparing is, well, technically, yes, we're comparing these two, but we could simplify this a little. Okay, so basically what we're going to do is pick the following. Okay, so again, this top one is the value if not exercised. And we don't, here's the thing though, we don't need to write max. Because if we exercise, that guarantees us that US minus K is positive. So basically, this is the comparison you're making when you make a decision between exercising and not exercising. So we can write this in a little bit slightly more compact form. The value of the option on each node, if it's an American call, can be written in a slightly simplified way. All right, so I'm going to show them to you. And, oh, for God's sake. Looks like we're back to X's here. I'd have to go through and straighten those out. Remember, K and X means the same thing. So in other words, for the FU that we were just analyzing, we're going to look at the greater of this amount, which is the value if not exercised. And this is the value. Remember, this is a put. Value if exercised. And it's the same for all of them. It's always the greater of the two. If it makes sense to exercise, we'll do that and we'll get this value. Otherwise, we'll leave it alone and we'll continue to have the value of the equivalent European option. Okay, so yeah, this is a lot to take in, but if we do an example, you'll see that it's not that difficult. So we'll start with an example of a one-period American call and American put. And so that would be right here. So we're basically taking the same data from sheet 1, and this time we're applying the test. Now, this is the formula that we'll be using. This is a one-period model, so we don't have to worry about exercising on the maturity date. That's understood. It might happen, it might not happen, but it's the interior nodes where we have to apply these formulas. So that's what this is right here. Now, I do want to point out here, though, this is an important detail. In fact, let me sneak this in here again. There is no guarantee that the option will ever be exercised on a binomial tree. So you might go through the whole tree and not find a single node where the option is exercised early. So don't be frustrated when that happens. It's possible that you won't get any early exercise. It does happen, especially when you only have a small number of steps. But the more steps you have, the more likely it is that the option will be exercised early. All right, so in fact, the reason why I mentioned that is because here with a single time step, if you notice, it does not get exercised. Because if you remember, these are the exact same numbers we had when this was a European option, where these were both European options. So it's kind of disappointing. I want you to see what that looks like, but I think in the next section, when we have two-period models, I think they do get exercised at least once. And then we can see how they're different from European options. Okay, so 2 and 4 are the same example, except, let me just double check everything. Yes, what's happening here is that we have a two-period American call and a two-period American put. And what we'd like to know is whether or not the option ever gets exercised. Now, I've highlighted the one node where the option actually does get exercised early. And you'll be able to see how much of a difference that makes in the price of the American put, as you can see. So here, if you notice, if you look through the whole tree, you're not getting any early exercise. How do you know? Because, well, first, I didn't put any yellow in there, but secondly, because each of these is simply equal to, first, these are the intrinsic values. And if you plug these into with your calculator, you'll see that that's the value if not exercised early. But down here with a put, there comes a node right here where the intrinsic value is more than, or the payoff is more than the European value based on these two nodes. And so we replace the price with a $5, because that's the price we would get if we exercise early. And so what that means is that this number is going to be a little bit higher, because in the downstate, it's worth $5 instead of wait. Trying to find the equivalent point on these trees. No, those are the 1 period models. Hold on. There we go. All right. So with the European, you know what, let me do this. Let me copy this. Remember, this is what the 2 period European model looks like. So I'll just copy this so that we can see them side by side. It's being I don't know what's going on here. It's being extremely stubborn with me. I wanted this to be moved over here. So you could see them side by side. Nope, one more. All right, anyway, so yes, here's where we are. So you see how here the payoffs are exactly the same. And here's what's different. In the upstate, we have the same number. In the downstate, when we're not allowed to exercise early, the put was only worth $2.04 basically. Here, we exercise early to get $5. Because the strike is 100, remember, and the stock price is 95. So here, if it's an American option, you've got to exercise it because you're basically doubling its value. And then you see that makes a big impact on the price of the option today. It goes up from 42 cents to 98 cents. So yes, this one time the option was exercised early, you can see it definitely adds to the value of the option. In this case, it basically doubled the price of the option. On the American tree, the option was never exercised. Now, here's a helpful hint, and we mentioned this when we we're looking at the boundary conditions. I'll just throw this in here as well. An American option, an American call that is, written on an asset with no underlying cash flows is never optimally exercised early. Okay, so therefore, it will always have the same price as the equivalent European call. And that's exactly what happened here. If you go back to sheet 3, you can see that the price was about not sheet 3, sheet 2. Oh no, this is a slightly different example. So we can't really compare them directly to each other, but this one we can see that they are different. All right. Anyway, that That's what I want you to see. So how in the world do you price American options? So again, it's very much like European options, except that what you have to do is at each node, each interior node that is, calculate not only this present value of the expected payoffs or the expected future values, but also consider the possibility of early exercise. Okay, so that's why some of these nodes, you'll get early exercise and that will have a significant impact on the price of your option. So that's that. All right, so that's done. Now we can move on to this week's material, which is a little bit different because we're focusing more on the risk management, where what we're considering is risk measures that are designed to help us understand how risky options really are. All right, now options are very complicated securities. You may have heard of the word beta that's used to describe the risk of a stock. It's a single measure and it can be very useful. But options, or the prices of options, are affected by many different variables in the marketplace. And so it stands to reason that we need more different kinds of risk measures to explain the properties of an option than for a stock. And so the risk measures that we see typically used to describe options are collectively known as the Greeks because they're all named after Greek letters, except for one of them. We'll see that one when we get to it. So we'll be looking at the so-called Greeks. We need to know what they are, what they're telling us, and how to calculate them. And ultimately, what are they used for? Well, for hedging risk. In other words, it helps us understand how much risk is in our portfolio, what kind of risks are we exposed to, and potentially strategies for getting rid of that risk. Okay, now, these are measures that help us understand the sensitivity of an options price to changes in underlying variables. Now, if you remember, just as a quick reminder, before we carry on here, the price of an option depends on several variables, such as the underlying asset price, the volatility, the time to maturity, and the risk-free rate. So if any of these changes, the value of the option will also change. And so these Greeks are designed to help us understand what could happen to the price of our option if, for example, the asset price goes up, or volatility goes up, or the risk-free rate goes down, or the time to maturity shrinks. So that's what these Greeks are for. So here they are. Now, there's more than these, but these are the most standard ones. So we have 5. Now, somebody along the way, whoever created these names, made a bit of a mistake here. They chose the name Vega to represent the sensitivity of the option to volatility. Unfortunately, though, Vega is not a Greek letter. So sometimes you hear it referred to as lambda, or occasionally even kappa, because there's no letter associated with Vega. I guess somebody thought it sounded cool. Vega is actually a star in the constellation Lyra in the southern hemisphere, and I suppose somebody thought it was cool to call the Vega measure, the volatility measure, Vega. So of all these, it's the only one that's not actually a Greek letter. But the others certainly are. So what are they all about? Well, the delta of a, now we're going to have to make a separate formula, as it turns out, for calls and puts, because they typically behave very differently. So for example, oh, and by the way, in case you've forgotten, this is the Greek letter delta. In fact, why don't I give you a quick review here while we're at it. That's delta. That's gamma. This is theta. Lambda is this thing. And then finally, rho looks something like this. just in case it's been a while since you encountered Greek letters. And just a quick reminder, all the Greek letters have both an upper and a lower case version. So you may have seen other variants of these letters, but these are the uppercase versions of delta, gamma, theta, lambda, and rho. So the call delta, where I have a subscript of C here, represents the change in the call price with respect to a change in the asset price. In other words, if I want to know if I have an option on a stock, a call option on a stock, what can happen to the price of my option if the stock price goes up by $1? It's a pretty important thing to know because you never know what can happen in the market. And, let's face it, if I'm keeping options in my portfolio, I've got a lot of risk coming from those options, and I may be using them as hedging instruments. So it's awfully important to understand how they react to changes in the marketplace. So this is important information. It's not just an academic curiosity. Options traders on Wall Street use these numbers every day. Now, let me just get rid of some of this old drawing here so we can start all over again. Not that this is invaluable, but I want to start again with you. Okay, now what are we seeing here? This represents, the red part is the payoff to the call. And we did this a couple weeks ago. Remember, the way this works is that the payoff is 0 down here. And then once we hit the strike price, after this, the payoff goes up on a 1-for-1 basis with the stock price. This is the payoff. Now, what is this black line? This is the actual market price of the option. And the market price, unless it's the last day of trading, is always greater than the payoff. And the gap between the two right here is the option's time value. So in other words, if the strike price is, let's say the stock is selling for 110 and the strike is 100, well, the intrinsic value or payoff is 10. If the call price is 12, the time value is $2 because it's 12 minus 10. In other words, those last $2 are coming from the idea that the option still has some potential to move more deeply into the money. So the deltas are taken from this market price curve. The deltas are actually the slopes of the market price curve. So for example, down here, the curve is basically flat. So that delta, it may not be 0, but it's very close. Up here at the other extreme, the delta is close to 1. And then in between, right at the money, the delta is right around 0.5. So you can see the delta itself depends on how deeply the option is in or out of the money. I hope that makes sense, because if the option is very deeply out of the money, like it is down here, let's say that, for example, if the strike is 100 and the stock is at 50, you're very, very deeply out of the money. It's very unlikely the option will actually be exercised. So if the stock price goes up to 51, that doesn't add a whole lot of value to the option, because it doesn't really change the fact that it's unlikely that the option will be exercised. Whereas up here, if the strike is 100 and the stock is at 150, and then it goes up to 151, that should add roughly $1 to the value of the option, because it's almost guaranteed to be exercised. Now, right here, the option is basically sitting on the fence between finishing in and out of the money. So if the price of the stock goes up by $1, that only adds roughly 50 cents to the price of the option, because you're still sitting on the fence between finishing in and out of the money. All right, so now, of course, there's a formula for doing this, which is actually taken from the Black-Scholes model. It's a little, no, it's not that complicated. Oh, by the way, we're going to introduce some notation here. No, maybe we're not. Let's skip ahead. All right. Let's just jump ahead to the put. Now, the put, you can see the definition is very similar. It's now the change in the put price divided by the change in the asset price. What is different here, I think I'll check that out later on. What's different now, though, is that because an increase in the stock price reduces the value of the put delta will actually be negative. The call delta will be positive. The put delta will be negative. And in addition, there's a specific limit to how high up or down it can go. But just remember, the call delta is positive. And the put delta is negative. And that's because when the stock price goes up, the call price goes up, the put price goes down. But the basic idea is the same. Now, and you can see why. I've got a graph here which shows the European put. Remember now, the European put is the one that could end up with negative time value. But if you look at it carefully, you'll see that the deltas make perfect sense. Okay, so this is our market price once again. And the red is the payoff. And the delta is the slope of the curve. Now here the slopes are all negative, aren't they? Yes, because the curve is moving down towards the right. So the range, you can see the delta can't go beyond -1 on the upside or below 0 on the downside. All right, so why don't I summarize this for you? The call delta, which I'll remember we wrote as delta C, cannot fall outside the range from 0 to 1. The put delta has to be between -1 and 0. So that's a quick summary right there. Now, how do we calculate the delta? The graph is fine, but it's not telling us how to actually come up with numbers. So if you go back to the Black-Scholes formula and you look at it carefully, you'll see that, well, let's see right here. This is the Black-Scholes formula, of course. The change in the call price when S changes. So in other words, if S rises by $1, then this entire term, C rises by ND1. So this ND1 is actually the call delta. This mysterious ND1 term that we saw earlier is actually the call delta. And when we calculated before, you notice it was always a fractional value. And so, for example, well, we're going to see more of that later on, but let's see. Oh, this is the one we had earlier. When we had, there was a strike, an option with a strike of 50, a stock price of 52, the risk-free rate was 2%, the volatility was 30%, and the time to maturity is 1. And we calculated that ND1 was 0.6359, and that turns out to be the delta. So therefore, for this particular option, if I raise the price by $1 of the stock, the option price should go up by roughly 63.59 cents. Now down here, I did a little experiment. As you can see, these are the original values. I actually raised S2 by $1. And so based on the delta, the price was predicted to go up to 826.89. It actually went up to about 828.08. Okay, so it's off a little bit, but that's because it's it's not a huge change, but if we change it by a nickel or a penny, then the price change would have probably been exactly the same as our prediction. Anyway, what about the put? All right, well, let's skip over all this stuff. The put equals ND1 minus 1. Or you can write it as delta P is delta C minus 1. Okay, so that's how they're related to each other. So again, this example we had earlier, this is the first, actually we used this for the Black-Scholes model. We discovered that ND1 was 0.6359. And so the equivalent European put, meaning that it has all the same features except that it's a put, would have a delta of 1 minus that, or actually that minus 1, which means negative 0.3641. Now, here's something interesting. I have a couple of graphs here. It turns out, as we saw in the graphs up to this point, let's go back and revisit them for a second. You noticed that the delta depends on the stock price. In other words, if the stock price exactly matches X, the delta should be right around a half. As the stock price goes up, the delta rises. As the stock price drops, the delta falls. With the put, it's the other way around. Okay, with a high stock price, the put should fall close to 0. With a low stock price, the put should have a very negative value. So the graphs that I'm about to show you show the relationship between the delta and the stock price. So for example, right here, now remember the delta is 50. The strike price is 50. So what's happening here is that now on the vertical axis, I have delta. And down here I have S. And so you can see when the option is out of the money, the delta is very low and it stays low. It takes a lot of increase in the stock price for it to start to go up. And once it starts rising, it starts to rise fairly quickly. It reaches about 0.5 when we hit the strike price, and then it continues to rise, although you can see it's rising fairly slowly now, and it will never break through that 1. So basically the curve increases very slowly, then very quickly, and then very slowly. So it tapers off at 1 and 0. That's what the call delta looks like. That's how it's related to the stock price. Now for the put delta, I did the exact same thing. And because the put delta is bounded between 0 and -1, the axis is a little bit different. The vertical axis starts at 0 and works its way down to -1. So let me show you what that looks like and say, wait a minute, that looks very familiar. It does have the exact same shape. And there's a reason for that, because they're only different by a constant. So the shapes are exactly the same. The only thing that's different is the size of these numbers. They're negative instead of positive. Now, you'll see why this is important later on. This is helpful to us because it'll help us to find another one of the Greeks. But it's also interesting to notice how this works. That way, if you have a portfolio on, or you own an option on a very volatile stock, you get some sense of what might happen to the delta if the stock price moves around a lot. Now, what if the stock does in fact provide, or the asset as in general, has some kind of cash flow that belongs to the owner of the asset, and that cash flow is paid out on a continuously compounded basis? So you might recall that the modified Black-Scholes formula looks something like this. And so because of that, we have to make a slight change to our calculations. We introduced this piece, which wasn't there before. It's only a slight change because e to the minus qt is likely to be a number very close to 1, like 0.99 or 0.98 or something like that. But it's important. We need to understand how the potential cash flows are affecting the value of our delta. All right. Now, here's a bit of a side detour here. Delta can be applied to other assets besides options. For example, a forward contract, which you recall is an agreement between two counterparties to buy or sell an asset in the future. Now, in a way, an option is really just like a long forward forward contract where you can change your mind. So if you look at this payoff to a long forward contract, you can see that if I wanted to know the delta of this forward contract, it would just be 1. I'll call it delta F, because these will both change by the same amount. If the stock price goes up by $1, the value of my contract goes up by $1 and vice versa. So this is a simple case. The value of my forward contract changes on a 1-for-1 basis with the stock price. Now, it turns out, and for a put, now this is a short forward contract. By the way, I just want to remind you, a long forward contract gives you the right to buy, or not the right, the obligation to buy. And then the equivalent short contract, which is the obligation to sell. If you look at the change in F over the change in S, you'll see that that will be equal to -1. So if the stock price goes up by $1, the value of my forward contract goes down by $1. And if we have an asset where there's a cash flow involved, then we have to make a couple of slight changes. The delta of the forward contract, the long forward contract, sorry, is this instead of 1. And for the short forward contract, it's this instead of -1. Now, here's an interesting question. What's the delta of the stock? Ooh. Does the stock have a delta? Okay. Well, technically it does, but the way you'll see when I write out the definition. So we're assuming up to this point that every one of these derivatives has had an underlying stock. The delta of the stock, which I'll call delta S, would be the change in the stock price due to a change in the stock price. So by definition, it would just simply equal 1. I mean, it's a silly thing to think about. How sensitive is the stock price to the changes in the stock price? Well, if the stock price goes up by $1, the stock price goes up by $1. So this is defined to equal 1. All right. Now, the delta of a portfolio of assets, in particular options, but other assets as well. The nice thing about this delta measure is that it is a linear measure, which means the delta of a portfolio is the weighted average of the deltas in the portfolio. That's very helpful. So if I add assets to my portfolio, it's very easy to figure out what the new delta is. Okay, let me show you what I mean by that. Oh, here we go. So this is this little pie means portfolio. This is the weight of asset I, and that weight means simply what proportion of the portfolio is invested in that asset. And this is the delta of asset I. So we just add up the weights times the deltas, and we have the entire portfolio delta. Interesting. Now, as we've seen, a put has a negative delta. So if we combine the right assets into this portfolio, we can find ourselves with a portfolio whose delta is literally equal to 0. Okay, so in other words, if we choose our assets carefully, we can find ourselves with a portfolio whose delta equals 0. And if the delta equals 0, that means the asset, the value can't change. And we consider it to be risk-free. So in other words, if you're a trader of some kind and you have a position in stocks, you can get rid of all of your risk by holding the right combinations of options that give us this portfolio with a delta of 0. And in fact, this is such an important idea in finance that these types of portfolios are referred to as being delta neutral. No delta, that means no risk. All right. So in other words, if I keep adding more assets to my portfolio in such a way that the total delta is zero, I've created a risk-free or perfectly hedged portfolio. And that might be exactly what I want if I expect the market to really get ridiculous. All right, now let me show you a quick numerical example of this. What if we own a portfolio with 100 shares of stock? The portfolio delta must be 100 because remember, each share of stock has a delta of 1. There's a put out there somewhere that we can buy with a delta of negative 0.5. So if I were to buy 200 puts at a delta of negative 0.5 each, the existing shares have a delta of 100. Then my puts would have a delta of negative 100. I would end up with 0 for my delta, or a perfectly hedged portfolio. So no matter what happens to the stock price, my portfolio value will not be changed. Okay, that's an important idea because sometimes that's exactly what traders try to do. Rather than selling those stocks before the market bounces around or crashes even, they might decide to create a delta neutral portfolio, but then they have to know how to do it. And of course, it depends on what options they buy for that portfolio. But if it's done carefully, they could create what's called a delta neutral portfolio and end up with no risk. Okay, now, if we go back and look at our list of Greeks, you'll see that the second one is something called there we are, gamma. Now, the name, by the way, the names of these things were kind of randomly chosen. I don't know what the thinking was, but gamma is interesting because gamma itself is actually a derivative of delta. In other words, if you look back at this delta graph, if the stock price keeps changing, the delta keeps changing too. Okay. So what the gamma is trying to capture is how much the delta is affected by changing in the stock price, which means that the gamma is actually the slope of this curve. It can go from 0 to 1 and anything in between. It can't be negative, okay? Because if you increase the stock price, the delta will go up automatically. So the gamma, basically, why do we need the gamma? So that if we have a delta neutral portfolio and we're worried that the market is really going berserk, our delta neutral portfolio might not stay delta neutral for very long if the stock price moves around sufficiently. So the gamma is a measure of how sensitive our deltas are to stock changes or stock price changes. And that's important. It can give us a lot of insights into how risky our portfolio really is. And if it's too risky, it gives us insights into what we can do about it. So let's formally introduce this here. What is the actual definition of gamma? Is the change in the call delta with respect to a change in the price. Oh, here I couldn't resist the temptation to show you that, yes, this is actually the uppercase Greek letter gamma. To the right, we have the lowercase version. Looks like a fish standing on its side, basically. So we'll use the uppercase version, and it's representing the change in the call delta with respect to a change in this case, the stock price. And as I showed you, this number cannot go past, go below 0. Now the put gamma is exactly the same idea. It's a change in the put delta with respect to a change in the asset price. Now, here's where it gets interesting. You might think that one is positive and one is negative. But when we looked up here at these graphs, you saw that they have the same slopes. The gamma, remember, is the slope of this curve. If the slopes are the same, that means the gammas are the same as well. So therefore, we conclude from this that a call and a put with the same strike, maturity, and underlying asset have the same gamma. And the gamma is positive. Now that's something you weren't expecting, I bet. Okay, now just like with the delta, there's a formula for this. We don't need to overdo it with the formulas, but if you look in the spreadsheet for this week, what I have done is I've taken, well, this stuff is here from last time, but in sheet 2, I've got this example we had when we were doing Black-Scholes, and down here on the side, I've gone through and calculated all of the Greeks for the call and the put based on the slides. So they're all here. Don't worry, we'll get to them all. And you notice the call and the put gamma are both positive, and they're the same number because it's the same option. And it's also a very small number. But this is the formula that I've been using. So this is how it's derived from the Black-Scholes formula. And by the way, if you're wondering about this n prime of D1, you might recall that n of D1 would mean this. N prime of D1 is a little different. That actually represents the height of the curve at that point. Or you can think of it as the sensitivity, or how much is the area changing from D1 to the next point under the curve. So we need that to calculate the gamma, and Excel has that formula built into it. And so it's easy to calculate the gamma once we know all the other information, because basically what you're doing is calculating n prime of D1 divided by the stock price, the volatility, and the square root of the time to maturity. So you saw in the slide, in the spreadsheet, these are both about 0.024, and here this explains where it came from. And by the way, the Excel formula for n prime is called norm. Well, actually, here's what you're doing here. And so this, if you think of this as x, so this is non-cumulative. We normally put a 1 there for just plain n of x. You would have norm.dist, norm.s.dist of x and 1. Okay. Now I think I've got a, oh, and one more thing. What does this actually mean? It means that if the stock price goes up by $1, the call delta and the put delta goes up by 0.024. That's what it actually means. So the fact that it's 0.24 means that if the price of the stock goes up by $1, the delta goes up by 0.024. All right, so let's just take a quick look at a graph of gamma. Now we don't need two separate graphs of the calls and the puts because we know that they're the same. But you can see it's definitely positive. It's not a very large number. This one doesn't go above 0.03. It's kind of like a mountain, but it maxes out right around the strike price. After that, it falls off very quickly. So this is the call or put gamma. It doesn't really matter. All right, and then like with all the other cases, we'll see this throughout the chapter. If the asset provides some kind of a cash flow to the owner, we have to make a subtle modification to the gamma formula. It's the same. It's always the same. You're multiplying by e to the minus qt power. So that's here. Yeah, there it is. And again, it's a very subtle difference. This is probably going to be very, very close to 1, just not quite. Now, here's an interesting twist. A portfolio can be delta neutral. It can also be gamma neutral, which means that not only are changes in the stock price not changing the delta of the portfolio, or the value rather, but the deltas themselves are staying the same. So if we can manage to achieve a portfolio that's both delta neutral and gamma neutral, then there's really and truly no risk. Okay, even a large change in stock prices will have no effect because the deltas themselves will not be changing. So the portfolio will remain delta neutral no matter what happens to stock prices. All right. Now there's 3 more. There's theta, vega, and rho. They're not quite as important as the first 2, delta and gamma. We're going to look at them all anyway. We want to understand what they tell us, how they're calculated, and we want to look at their graphs so we can get a feel for what exactly they're trying to explain to us. They're all very interesting and they have their place, but definitely delta and gamma are the more important of the 2. So I'll tell you what, why don't we save these for after the break? And when we get back, we'll take a look at theta, theta, vega, and rho, and we'll understand what they're all about. And then we can briefly look at the spreadsheet. And what I've done here is, you can see, I went through and did a bunch of experiments where I showed what the predicted changes were in the stock price and what they would have actually been compared to those predictions based on the Greeks. And you'll see that in most cases, the predictions are quite good. All right, so let's knock it off for a bit. When we get back, we'll be looking at theta, vega, and rho. Okay. Okay. All right, it's time for theta. So a theta represents, oh, by the way, let me just go quickly review real fast something we said earlier. When we're looking at the payoff, yeah, here it is. The black line is the market price of the option, and the red line is the payoff. The difference between the two is the time value of the option. Now, the one thing I didn't show you here is, let me do it now, is that, of course, as time evolves, this relationship will change as well. All right, so in other words, let's say we started here. And initially, all right, this is our payoff. So what we're going to do is look at the market price, let's say here. And this is when the option has, let's say, 3 months to maturity. What happens is as time elapses, the curve gets closer and closer to the payoff. Okay, in other words, as time elapses, we get closer and closer and closer to this payoff diagram, the red line that is. And then on the maturity date of the option, the market price curve matches the payoff. To the option. Okay, in other words, the red line would be the actual market price on the last day of trading of that option. So in other words, as time elapses, the time value of the option shrinks. So that on the maturity date, there is no time value. Okay. So in other words, on that very last day of the option's lifetime, there's no time value. So what the theta measures is how much time value is lost as time elapses. All right, where is it? Here we go. So it's the derivative of the option's price with respect to the time to maturity. It's referred to sometimes as the option's time decay because the time value approaches zero as the option approaches its maturity date. So in other words, the theta should be negative. It tells us how much the value, the time value declines as time goes by. So the formal definition looks like this. And remember, this is the Greek letter theta. This is the change in the call price, specifically the time value, as maturity, the time to maturity changes. Now, the time to maturity can only go in one direction. It can only shrink. Okay, we can't get further away from that maturity date. So this denominator is always shrinking. And so the change in the call price with respect to the change in time is what we're capturing here. Down here, oops. Well, there's a mistake. But this is actually the time value. Now, the formula for doing this is really messy. We're not going to spend too much time looking at it, but I mean, there's the, yeah, you get the idea. That's the formula for the call theta. And I did put that in the spreadsheet for you. And this is for the put theta. We're not going to spend too much time with this. But what we would like to do is note, by doing an example, which I did put in the slide, in the spreadsheet rather, you can see here that this theta for the call is negative 3.44. So the question is, what does that actually mean? Good question. Well, now that's by the way, that's an annual number. In order to convert it to a daily number, we're going to divide by 252, not 365, because we're assuming that there are 252 trading days or business days in a year. And so that means this is how much the value of the option declines for every day that we get closer to the maturity date. Okay, so in other words, if nothing else changes, one day goes by and the option price should fall by about 1.365 cents just because of this so-called time decay. Okay, so that's what we mean by time decay. And of course, the word decay means that it's getting smaller or shrinking. Loss each day that elapses or that goes by the time value of the option falls by approximately 1.365 cents. Now, that doesn't sound like much, but it can pile up after a while. So now for the put, we have something similar happening. The rate of decay is, it can be different. This depends to a large degree on how far out of the money or in the money the option is. You'll get that when you see the graph. All right, so this one is negative 2.54. It's not quite as bad. And that means roughly we lose 1 cent worth of value every day that goes by as we get closer to the maturity date. But remember, these numbers are really driven by how close we are to the strike price. Now, you might remember we did have a couple of peculiar cases when we started out. For example, a call for a European call that is deeply in the money, and I mean very deeply. Theta can actually be positive. But that's a very rare case. Most of the time, for almost every other scenario, the thetas are positive, negative for both calls and puts. All right, now let's take a look at the graphs. In these cases, the graphs are showing you what the theta looks like at a specific point in time for different stock prices. All right, so for the theta, call theta, remember the strike is 50 in these examples. The decay is most rapid when we're right at the money. Kind of like, it's basically, if you look at it as like an upside down gamma. Okay, remember the gamma was a big mountain, that it was only positive? This is a lot like an upside down gamma, where the peak value is right around the strike price, or in other words, where the option is right at the money. For the put, you'll see that it's similar, but not the same. Yeah, you can see it's similar. Let me just remind you, here's the call, and here's the put. They're almost reversed. Okay. So, but in both cases, you can see for the most part, they're negative, and they're most negative right around the strike price. And once again, I'll show it to you, but you don't have to worry about it. If we have an asset with a yield of some kind, the formulas are slightly different. Let me just quickly show you what they look like for the call and the put. Now look at that formula. That is the formula for the call theta. I don't like that formula. It's a nightmare. But it is luckily embedded in your spreadsheet here, so you don't have to type it. All the information you need is right here. So in fact, you can calculate any Greek for any option you want just by changing these 5 numbers. So you can think of this as a template for calculating Greeks. Also remember this sheet 2. Okay, sheet 1 is a review of what we did with the Black-Scholes model. And sheet 2 is our Greeks. So if you have an assignment, for example, where you have to calculate Greeks, this is all you have to do. Make the changes here, and you'll get your results right there. Okay. Now, sometimes for certain types of portfolio applications, we sometimes combine the Greeks. I don't know how helpful this really is, but this is how they're related to each other. All right, so the next Greek is the one that's not really a Greek letter, the one where somebody screwed up. But I think the motivation was they wanted a word that starts with a V to remind us that this is all about volatility. So the vega or lambda is the derivative of the options price with respect to the volatility of the underlying asset. So the next slide, you'll see that for a call, this is pretty much what you'd expect. The numerator is the change in the call value. The denominator is the change in the volatility. Remember, we use the sigma to represent volatility of the underlying asset. For the put, well, you get the idea. It's the change in the put value with respect to a change in the volatility. Now here, luckily for us, the vega formulas are pretty straightforward, certainly compared to theta, which is an absolute nightmare. All right, so let me show it to you. Now, here's an interesting twist. Just like with the gamma, the vegas for 2 options, a call or a put, that are identical in every way, will have the same vega. And on top of that, both of these vegas are always positive. Because I think I mentioned this once before, volatility is helpful to the value of an option. The more volatile the asset, the more valuable is the option. So just like the gamma, not only are these equal to each other for the same calls and puts, but they're always positive. And in fact, when you see the graph, you'll see a lot of similarities. All right. So first, let's look at a case where it's the same data we've been using. We want to calculate the volatile, or the vegas rather, and what we really want to do is understand what they mean. So remember all these details. This is the same option, the same case we've been using all along. If we plug in these numbers, we get for both the call and the put, 1953. So that sounds like a large number, but what it actually means is that a 1% increase in volatility adds 1% of 19.53, or 19.53 cents to the price of a call or a put. That's how we interpret that one. It's a little bit different than the other ones because it's based on percentages. Okay. Here's the graph. And like I said, it does look a lot like the gamma. The main difference here is that the numbers are a lot larger. Remember the gamma, it only went as high as 0.03. Here it's 20, but that's because they're interpreted differently. For all practical purposes, the graphs are identical to each other. And you'll notice, like all the other Greeks, the value tends to be greatest when we're right at the money, and then it falls off on either side. So in other words, the impact of volatility is the greatest on at the money options because they're sitting on the fence between finishing in and out of the money. And so volatility can increase the likelihood that the option finishes in the money. So that's why the impact is so great here. And once again, if we have an option on an asset that provides some kind of a cash flow or yield, we have to make a slight adjustment to the calculations. And once again, you'll see that all we've done is added this term. In other words, wherever there was an S, it becomes SE to the minus QT. And in all the cases, in order to adjust our Greek formulas, this is what we're doing. All right. Now, the last of the Greeks is rho. Rho, which looks like this, is the sensitivity of the options price to changes in the risk-free rate of interest. So yeah, sure. I mean, options values depend on interest rates, just like every other asset in the economy. So formally, we'll define it. And just like all the other ones, the call rho is the change in the value of the call due to a change in the risk-free rate of interest. And then for the put option, we just replace the numerator with the value of the put. Now, the formula taken from the Black-Scholes formula is very straightforward. It's not hard. In fact, really, the only hard one is theta. The rest of these are pretty down to earth, you can see. But what you will notice is that unlike with Vega and Gamma, the signs of call rho and put rho are always different, just like with the deltas. And in fact, in that sense, it's exactly the same. The rho of a call is always positive, and the rho of a put is always negative. All right, so using the exact same example we've been using all along, let's do some calculations. The call rho is 25.43. And you notice here, we're interpreting this similarly to the Vega. If there's a 1% change this time in the interest rate, the call goes up by 1% of this 25.43, or about 25.43 cents. All right. Now for the corresponding put, the rho is now, as you can see, negative 23.58. And now we know how to interpret that. If the rate of interest or risk-free rate goes up 1%, the price of the put actually goes down by 23.58 cents. All right, so just to summarize again, for a call, the rho is always positive, and for a put, the rho is always negative. Now, when you see the graphs, they should remind you of something we've seen before. Okay, let me show you the graphs. Okay, give you a second to catch up. So let's take a look at the rho of the call. Now, you notice how it starts at 0. It looks a lot like the call delta, doesn't it? It sure does, except that the numbers are different. The call delta is bounded between 0 and 1. The call rho doesn't have an upper limit. But the shape is exactly the same. And guess what? Look at the put. This one has to be negative, but still, it's the same shape. So this does look a lot like the relationship between the call delta and the put delta, except now that it's rho. Anyway, I've helpfully put together a little chart for you so that you'll remember what the signs look like. And remember the theta, we have some potentially weird cases, but basically these should all be negatives. So in other words, for a call, European or American, higher stock price raises, when the delta is always positive for a call, negative for a put. Gamma, it's always positive. Theta, it's almost always negative, except for those weird cases, which only works for European options, by the way. The vegas are always positive, and the rhos, like the deltas, are positive for calls and negative for puts. All right, so now what we're going to do is take a look at our spreadsheet, and we have all these calculations. These are just the formulas that we saw on the slides. But what I did here is I went through and like I said before, I did a bunch of predictions. What I did was I actually changed the stock price to see how that affected, or actually I didn't change, the stock price, except for the delta, yes. But for the others, I changed the underlying variable. Like for example, down here, I changed time, the theta, and I changed volatility for the vega, and I changed the risk-free rate for the rho. And the purpose of this was so that I could say, well, listen, I'll use the Black-Scholes model to figure out what happens as a result of these changes. So let's start here. Okay, now, we had this example many times. The stock price was 52 and the call price was 7.633. I raised the stock price to $53. The actual change is here. The one predicted by the delta is here. And you can see, they're pretty close to each other. They would be even closer to each other if the stock price went up by a smaller amount. With the put, you can see the difference between predicted and actual. Again, it's pretty close. I'm sure that difference is a very small percentage. Let me go just quickly check this out. Let's see, hold on. Oh, it's less than 1%. It's a fraction. It's like 0.2% difference. So that's pretty impressive. Anyway, I did the same thing for all the other ones. And for this one, I changed the stock price. No, actually, I changed the delta. And I calculated the impact on the gamma. No, actually, sorry, I changed the stock price and I used the predicted change in the delta from the gamma. And you can see those are very close to each other. Here I let the time change a little bit. And these are the differences between actual and predicted. Down here, I changed the volatility by 1%. They're all very close to each other. And then finally, I changed the risk-free rate by 1%. And yes, they're all very close. Wow. So they seem to work very well. And this is why they're so heavily used on Wall Street, because the traders have to know exactly what they're doing, as do the portfolio managers and the risk managers and all the rest. They need to understand how the changes in the marketplace are affecting the Greeks, which in turn tell us how the option prices will react. Okay, now, let's see, what do we have in this folder? I didn't write an assignment for this week. As you know, I haven't handed back the old ones either. I'm still wrapping up my final exams in the daytime, but sometime this week I'll have them back to you. And then week 8, I don't think no, I don't think so. I think we've already finished all of our assignments for the semester. It's just a question of me getting them back to you. So next week we're introducing risk management itself, where what we had today was a taste of it. We're introducing this value at risk methodology, which is an important idea in finance because it helps us measure how much risk our portfolio has. And it also deals heavily with how derivatives can reduce our risk. In other words, it gives us another way of measuring how much risk derivatives can reduce in our portfolios. And so that's why it's pretty closely related to derivative securities modeling, because we often see derivatives used as hedging instruments. So with the value at risk methodology, we can determine how much the derivatives are actually reducing the risk of our portfolios. So we'll start that next week. And then we'll actually be done with the course, sadly enough. This is such a big area. We could have done 2 or 3 entire classes and not even scratch the surface of derivatives. It's such an intense, deep area of study, but we can only do so much in one course. So we'll wrap it up next week with our discussion about value at risk, and I will get all of your assignments back to you. And in the meantime, we're done with your assignments. There are no more. And so I'm sure you'll be relieved to hear that. And I will, of course, send you the notes we did tonight. And even though it's a little early, I guess we deserve a little bit of a break tonight. And I'll see you all next week.
Thank you, Professor.
See you later. Okay. All right. Bye.